Okay, so in this video, we will find all values of x for which the following power series converges, therefore finding the domain of this function. Now every time we look for the convergence of a power series, no matter what the coefficients of the power series may be, there is always the term x minus its center to the nth power that allows us to use either the ratio or the root test. In this video, we will use the ratio test, but feel free to do as an exercise the same problem with the root test. And again, notice here that the center of the power series, x0, is negative 3. As the term here to the nth power is x minus the center, so since it is plus 3, the center must be negative 3. So we are summing these terms from 1 to infinity, so this is our an when it comes to the ratio test. So, applying the ratio test, we look at the limit as n tends to infinity, an absolute value of an plus 1 over an. To obtain an plus 1, simply replace the subscript n by n plus 1, which will give you the term 2 to the n plus 1 with the root of n plus 1 times x plus 3 to the n plus 1. And dividing by n is the same as multiplying by the reciprocal, so multiplying by the root of n over 2 to the n x plus 3 to the n. And now we can simplify it. So, 2 to the n plus 1 over 2 to the n, subtracting n plus 1 minus n is 1, so 2 to the n cancels. And we're left with simply 2, but as 2 is positive, it can be moved out of the absolute value. We have the root of n over the root of n plus 1. We can combine both as the square root of n over n plus 1. As this is once again positive, this can be pulled out of the square root as well. These terms are now taken care of. And we can of course simplify x plus 3 to the n plus 1 divided by x plus 3 to the n. Well, n plus 1 minus n is 1, so this cancels, and we're left with the power of 1. But as x plus 3 could be negative, we have to keep the absolute value on this term. The limit will become trivial if we think of, inside the square root, multiplying top and bottom by 1 over n, which will give us 1 over n times n is 1 over 1 over n times n plus 1. Well, n over n is 1, plus of course 1 over n, times x plus 3 in absolute value. The limit now is trivial. As n tends to infinity, 1 over n tends to 0. So we'll have here the root of 1 over 1, root of 1 which is 1, and so we're left with 2 times x plus 3 in absolute value. Another question is, well, where do we go from here? Well, remember, we are trying to find all values of x for which the power series converges, so we need that this limit be less than 1. Strictly less than 1. This is when the ratio test returns absolute convergence. So if we can find all values of x that satisfy this inequality, then the power series will converge absolutely from the ratio test. So we can now isolate for x. Well, we can multiply across by 1/2. As 1/2 is positive, it preserves the direction of the inequality. So x plus 3 is less than the half, 1 over 2, and if x plus 3 in absolute value is less than the half, then x plus 3 must lie between negative 1/2 and positive 1/2. As we're saying, the size of x plus 3 is no more than 1/2. We want to isolate for x, so we have to subtract 3 across both inequalities, which will leave us with, well, negative 1/2, negative 3 is negative 7 over 2. x plus 3 minus 3 is x. 1/2 minus 3 is negative 5 over 2. So for values of x that lie between negative 7 over 2 and negative 5 over 2, this inequality is satisfied. Therefore, by the ratio test, the power series converges absolutely. Let's visualize this onto the real line. And recall that the center of the power series is negative 3. And you will understand why this is called the center as soon as we consider the endpoints of our interval. So, the right endpoint, negative 5 over 2. If you want, of course, this is negative 2.5. So slightly larger than negative 3. The left-hand point, negative 7 over 2. But of course, negative 7 over 2 is negative 3.5. And so you see, the center of the power series was negative 3, and the center of the power series is the center of the interval where we have convergence. And this is, of course, why this is called the center of the power series. So again, on this interval, because the limit of the ratio test is strictly less than 1, we know by the ratio test that we have here absolute convergence of the power series. Now, what if we move away from the interval? Then what happens? Moving away also from both endpoints. Well, if we move away from this interval, then we are violating our condition, which will mean that the limit coming from the ratio test will now be strictly larger than 1. Well, the ratio test says that if the limit is larger than 1, the series diverges. So away from our interval, excluding the endpoints, we have divergence of the power series. And the same goes to the left. Also divergence, as again the ratio test will return a ratio that is strictly larger than 1. The only question left now is what happens at the endpoints. And why is this an interesting question, or a non-obvious question? Well, plug in, say, negative 5 over 2 in here. You have negative 5 over 2 plus 3, that's positive 1/2, times 2 is 1. And so you see that the limit of the ratio test is equal to 1, and in this case we know that the ratio test fails. So the series may converge or diverge at the right-hand point of our interval. Well, negative 7 on 2 is negative 3.5, plus 3 will be negative 0.5, and absolute value is 0.5 times 2 is 1 again. And so you see at the left-hand point, the limit of the ratio test is also equal to 1, which also says that the test fails at negative 7 over 2. So once again, at the left-hand point, the power series may converge or diverge. And this is the only two questions that are left. What does happen to the series at the end points? And now we can simply check in both cases and plug it in, right? As we know that inside of this interval, we have absolute convergence. Outside we have divergence. At the end points, as of now, it remains a question. Now notice here that from negative 3, the center of the series, the center of the interval, we can walk in both directions by 1/2 and still have convergence. So here, the radius of convergence is equal to 1/2. If you recall, the radius of convergence is how far from the center can you walk and still have convergence. The answer here, 0.5 to the right, 0.5 to the left, which is of course 1/2. So let's look at the endpoints, and let's remind ourselves of what is the original power series. Our power series, summing from 1 to infinity, 2 to the n over the root of n times x plus 3 to the n. And now we're asking, or we are left with the two questions: will this power series converge when x is negative 5 over 2? And will this power series converge when x is negative 7 over 2? So we just have to plug it in and see what kind of series we are dealing with. So let's look at the left-hand point first. It's negative 7 on 2, which we know is negative 3.5. So let's replace. The coefficients stay the same. And now we are replacing x by negative 3.5. Well, negative 3.5 plus 3 is negative 0.5, which I will write as, of course, negative 1/2. Let's simplify. Negative 1 to the n, negative 1 to the n, 2 to the n. We can cancel the 2 to the n over itself, and we're left with a very simple series. Negative 1 to the n over the square root of n. And this is a very simple alternating series. Because of the negative 1 to the n, the bn, the positive part of the sequence, is 1 over root of n. This is clearly decreasing as n increases, and obviously 1 over root of n tends to 0 as n tends to infinity. So this series converges by the alternating series test. So we do have convergence of our power series at the left-hand point of the interval. Well, what about now the right-hand point, when x is negative 5 over 2? Which is of course negative 2.5. Once again, the coefficients stay the same. Replacing now x by negative 2.5, but negative 2.5 plus 3 is 0.5, which I will of course write as 1 over 2. All to the nth power. Once again, let's simplify. One to the n is 1 over 2 to the n. 2 to the n cancels. And here, instead of writing 1 over root of n, I will write 1 over n to the power of 1/2. Because now it is clear that this series is a p series where p is equal to 1/2. And 1/2 is less than 1. But if you recall, a p series will only converge if p is strictly greater than 1. As this is not the case, this series diverges by the p-series test. And so we're done. Our power series converges inside the open interval from negative 7 over 2 to negative 5 over 2, and it converges at the left-hand point, diverges at the right-hand point. So in the end, we will call this interval I, closed at the left-hand point because we do have convergence. So negative 7 over 2, all the way up to negative 5 over 2, but at the right-hand point, the series diverges, so we have to exclude the right-hand point. And you see this interval contains now all values of x for which the power series converges. And this is why, of course, this is called the interval of convergence. which of course you could think of as the domain of this function. This power series only converges for values of x that are in this interval, left point included, right point excluded. Therefore, on this interval, the power series is a function. And recall that also the radius of convergence was 1/2, and the center of the series was -3. And now we have everything. So to summarize, we looked at this power series. The power series only converges for values of x that are between -7/2 included up to -5/2 excluded. Therefore, this function has as its domain the interval I. The center of the series was -3, the center of the interval of convergence. And because we could walk from the center in both directions by 1/2 and still have convergence, the radius of convergence of the power series is 1/2. And that's it.